Hi, everyone. Welcome back for part two of Factorial ANOVA. In this section, we're going to be focusing on becoming familiar with the differences between main effects and interactions, and probably talk a little bit about interpretation of main effects and interactions. One thing that we're going to keep in mind during this section is that we are still not yet talking about statistical significance. Our goal here is simply to identify the types of effects that are occurring in a factorial ANOVA and start getting what we might call an eyeball interpretation of what effects might be in particular examples. We're going to be eyeballing figures and graphs and numbers rather than conducting actual statistical tests, which will come later. But our goal right now is not to discuss the achievement of statistical significance, but rather to discuss just the types of effects that can occur in a factorial design. So let's remember that factorial designs are those in which you have more than one independent variable. Typically, we're going to have two, but you can technically have as many as you'd like. They just add levels of complexity as you increase the number of independent variables. And at some point, you're going to max out on how much complexity you really might want in an experiment. It will become overly complex. So typically, you see these with either two independent variables or three independent variables. We call those variables factors. They're the things that put our participants into separate groups. They can be true independent variables, which are things that we manipulate actively in the world, or those factors can be subject variables. These are still independent variables. We might want to call them quasi-independent variables because these are already existing variables about a person, such as their sex, political affiliation, religion, or race. They create groups and put different people into different groups, but they're things that researchers can't either ethically or even possibly manipulate. We can still use them as factors and independent variables, but we just want to keep in mind the difference between sort of looking at something that the researcher is unable to control, a subject variable, versus something the researcher has control over, which is a manipulated independent variable. So here we're going to talk about this idea of complexity. Why would you want to make things more complicated, right? Complexity is good only to a certain extent. If we had 35 independent variables, there's too much going on, right? Even though we technically could, we're not going to be able to make heads or tails of any kind of effect that's happening in that experiment. Now, the addition of maybe two or three independent variables does make things more complicated, but that complication is often where the sort of true nature of the effect lies. Because in a factorial design, we end up being able, as we mentioned in the last section, to look at the main effect of each independent variable, as well as the interaction of the independent variables with each other. So we prefer these designs because they're more efficient, first of all. So we can include two or three independent variables in a single experiment rather than having to run multiple experiments, which can take time, which can cost money, which might require more participants. And so rather than running a series of two or three independent separate experiments, we can efficiently run a single experiment that might include two or three independent variables. So this allows us to look at our main effects, right? The impact of each variable in isolation, just as we would in a simple experiment. Factorial designs are more informative because of this interaction effect or interaction term that they're going to allow us to investigate. This is a very special type of effect on the dependent variable that only exists in situations where we have two independent variables. If we were to run multiple experiments with a single independent variable in each experiment, then we would only be able to look at a main effect of each variable in isolation. In order to look at the interaction, which we're going to talk more about what that means, in order to look at the interaction, we must have a factorial design. We must include at least two independent variables. And remember, an interaction is the effect that requires us to say it depends. So the sort of silly illustrative example from last time was temperature and type of food, and the outcome is your liking of the food. If I asked you, do you prefer hot or cold food? You would probably respond by saying, well, that's kind of a nonsense question because it depends. The effect of temperature, independent variable number one, depends upon the type of food that you're eating, independent variable number two. So the true nature of the impact of temperature and type of food on likability is that they interact. It requires us to sort of merge information from both temperature and type of food together. It's this idea that the whole is greater than the sum of its parts. Right? When you investigate temperature and you investigate food at the same time, you get the effective temperature, you get the effective food, and then you get this emergent property of how the two interact together to provide this special effect on the dependent variable. So let's just go with our wordy textbook definition here of each of these effects. A main effect is the effect of one independent variable on the dependent variable while averaging across the levels of the other independent variable. Basically, when we say average across the other independent variable, what we're saying is ignoring the other independent variable. So if our two variables are temperature and kind of food, we could look at the main effect of temperature, meaning all the hot foods versus all the cold foods, and we're going to ignore the type of food for this effect. If we were looking at the main effect of type of food, we would say all the instances of ice cream versus all the instances of hamburgers, ignoring what temperature they are, right? That's what averaging across means. We're ignoring the other variable. So what this produces is a single main effect for each of our variables. So if I have two variables, then I have two main effects. If I have three variables, I have three main effects. If I have four variables, I have four main effects, an effect of each variable by itself. And then, of course, we have the interaction effect, or just interaction, which is when the effect of one variable depends upon the level of the other variable. So let's look at that language with food and temperature and type of food. The effect of temperature, hot versus cold, depends upon the level, ice cream versus hamburger, of the other variable of type of food. So whether or not you like ice cream depends upon whether it's hot or cold. Whether or not you like hamburgers depends upon whether it's hot or cold. This term, this phrase, or this word depends on or depends upon is the essence of an interaction. And we can think about it going both ways. It's not like the interaction necessarily goes in one direction versus the other. It's this combined effect, this sort of emergent effect of the two variables together. Okay, so let's think about another example. Let's stop talking about ice cream and hamburgers. Let's say that you want to measure attention. And we think that attention is impacted by distraction. So we could run a very simple experiment where we ask people to engage in this task here. We have an image on the left and an image on the right that are very similar, but there are certain things that are actually different. We can see that this handle on the cupboard at the end of the bed is different. This book is closed versus open in this picture. You've probably seen stupid little games like this on the internet, right? Spot the 10 differences between our pictures. And this is actually kind of similar to a task that we do in cognitive psychology called a change detection task. And change detection tasks are very good measurements of attention, which is a really important cognitive ability. So we're going to use this paradigm to measure people's attention, presumably people who are deploying attentional resources in a efficient or good manner are going to be good at this task. Then maybe they'll be accurate, they'll be fast. And people who are not deploying attentional resources very well will be bad at this task. They'll be slow and they'll be inaccurate. So we think that being distracted will impact your ability to deploy these attentional resources. So we create a distraction group, right? Maybe half of our people are in a room that's really loud. Maybe they're in a computer lab with other people. Maybe there's music, right? Something else is going on that we defined as distraction, versus our group of people who are under the condition of no distraction. And we can see that the no distraction group performs better. Great, simple experiment, one independent variable with one outcome. But we think that distraction is not the only thing that impacts attention. We think that the impact of distraction on attention will depend upon motivation, basically whether someone is being rewarded for their performance. So we think that attentional performance depends upon the sort of environment around you, your distraction, and it depends upon some sort of internal motivational component that we're going to manipulate with reward. So we have two independent variables: distraction, distracted versus not distracted are our levels, and independent variable number 2, reward, $5 reward for maybe winning the game or reaching some criteria of performance, versus a no reward condition where no matter what the participant does, they don't receive a reward. So this creates another, what we would call 2x2 factorial ANOVA or factorial design. Excuse me if I slip into ANOVA occasionally. That is the statistical test that we would use for this type of design. But we have a factorial design, and here we have a 2x2 design. So let's investigate what our results might look like and break down our main effects and interactions. So we see that we can depict this with bar graphs. You can do line graphs, you can do bar graphs. They're actually the same exact information. And we have our dependent variable. This looks like the different number of items spotted, right? How accurate were you in identifying the items that were different, whether you were distracted, which is on the left, versus not distracted, which is on the right. And then our different colors here signify this bar is people who did not have a reward. And then our little green, or I guess turquoise bars, are the bars where people were rewarded. So we have 4 bars because we have 4 experimental conditions or groups. We have a 2x2, which produces 4 cells, 4 groups. This first line depicts the score of people who were distracted and did not receive a reward. This second bar depicts the score of people who were distracted and received a reward. This third bar is people who were not distracted and received no reward. And this fourth bar depicts people who were not distracted but received a reward. Notice that the graph on the right-hand side of this slide looks different, but is actually the same exact information. All we've done is swap out which variable we've put on the x-axis versus which variable is distinguished by our colors. So the graphs look different, but they're actually exactly the same information. We can do that by breaking down sort of our scores across the two figures. So let's take this first bar on the left-hand side. This is the distraction no reward group. Looks like they have a score of like a little below 6. Maybe that's a 5. So let's find the distraction no reward group over here. Well, we have pink, which is distraction, and no reward, which is our left-hand side over here. And look, they have the same score, right at 5. We could go through and do that for each of our 4 groups, and we would find that each group has the equivalent score in each graph. The point here being, it doesn't matter which way you graph it. It doesn't matter whether independent variable number 1 is on the x-axis or independent variable number 2 is on the x-axis. The information will be the same. And the height of each bar represents the score of each of those groups. So if we want to investigate the main effect of distraction, remember that we average across the other independent variable. The other one is reward. So what that means is that we pretend like reward doesn't exist. We pretend like the different colors don't exist. And if we pretend like they don't exist, what that means is that we average across. We average the 2 distraction bars across reward to get a single distraction bar. We average the no distraction bars across reward condition in order to get a single no distraction bar over here on the right. So the graph on the right, it has become the sort of main effect depiction for distraction condition, in which we average all of the distraction bars together to get this, and we average all of the no distraction bars together to get this. So now our comparison of these 2 bars becomes our main effect of distraction. And it looks like there is a main effect. It looks like the undistracted, the no distraction condition, the participants that did not receive distraction, perform better. That makes perfect sense. You're better able to attend to tiny details when you're not distracted. Distraction reduces attentional performance. So that's our main effect of distraction, ignoring reward condition. And of course, we can do the same thing for reward condition. Notice we've put now reward condition on the x-axis over here on the left. We are going to average across distraction. Now, distraction is our color of our bars. So these 2 bars on the left-hand side, we average them together, and they produce our no reward bar. We take these 2 bars here on the right of our first graph. We average them together. We average across distraction. We average them together, and that produces our second bar that is just for reward conditions. We compare these 2 bars together, and it looks like we have a main effect of reward, such that participants who were offered a reward performed better than participants who were not offered a reward, who performed worse. So it looks like reward on its own impacts attention. So regardless of distraction condition, reward has a main effect. It has an individualized effect on our attentional outcome. Now, just because one variable has a main effect does not mean the other one has to have a main effect. And in fact, you don't have to have a main effect at all, right? You could design this experiment and neither variable has an independent effect. That's the way it works sometimes. That's fine. That's why we do the experiments. So you could have 0 main effects. You could have 1 main effect. You could have 2 main effects. It's just going to depend upon the question you're asking and the outcome of your research. So really quickly, we've sort of talked through a lot of this slide, but I want to give you maybe 10 seconds to sort of answer this middle question for yourself. If we had a 4x2x3 design, how many main effects would you have? If we had a 4x2x3 design, how many main effects would you have? Take 10 seconds and think about that really quick. So if we remember back to section 1 about our nomenclature, we know that the number of numbers tells us how many variables there are, and then the quantity of that number, so the number itself, tells us the levels of the variable. So here we have 3 independent variables. The first one has 4 levels, the second one has 2 levels, the third one has 3 levels. And so if a main effect is the impact of a single variable in isolation, it means we would have 1, 2, 3 main effects. So you have one main effect for each of your variables in a factorial design. Now, our interaction is this sort of combined effect. Does the impact of one variable depend upon the other one? These are much more difficult to sort of see or interpret. It's much more difficult for us to figure out what's going on in an interaction because it's the complicated part. Complicated is good, though, if it helps us see something that was there that we otherwise would not have seen, right? This effect emerges that we otherwise would not have been able to find. So we're going to spend some time here talking about interactions, and we're going to spend some time really breaking down how to interpret them in a later section. I believe section 3, the next section. So if we want to consider whether there's an interaction, we need to ask ourselves, for example here, does distraction have an equivalent effect on no reward versus reward? So basically, is the impact of distraction equal across reward, or is the impact of distraction unequal? Does it depend upon reward? So let's remember that our no distraction groups are turquoise, or maybe that's teal. I don't know. I'm bad with colors. Not colorblind, just color ignorant. Our teal bars represent the no distraction group, and our pinkish, maybe that's salmon, pinkish salmon bars represent the distraction group. So we can see here that in the reward condition, we have a small effect of distraction. Distraction reduces performance a little bit in the reward condition. But it still seems like that our distracted people, our salmon bar, our distracted people still perform pretty well because they're getting rewarded. They have this internal motivation to sort of maybe fight through the distraction and still do well. So distraction reduces performance slightly in the reward group. Well, what does distraction do in the no reward group? We can see that the introduction of distraction, so sort of moving from this bar to this bar, the introduction of distraction has a catastrophic effect on attentional resource or on attentional performance when you're not being rewarded. So here we have a small effect, and here we have a large effect of distraction. So we would say that there probably is an interaction here because the effect of distraction depends upon reward condition. When you're being rewarded, distraction matters a little bit. When you're not being rewarded, distraction matters a lot. Distraction really reduces your performance because you don't have that internal intrinsic reward motivation to continue to do well in the face of distraction. So this is an interaction. The impact of distraction depends upon the reward condition that you find yourself in. Okay. So notice that in a design with two independent variables, we had two main effects, one for each variable, and one potential interaction, right? Each of the variables, two of them interacting with one another. So if we had a 3x3 design down here at the bottom, we would still only have one possible interaction because we have variable 1 impacting or interacting with variable 2 potentially. That's it. That's all that can happen. We can have a main effect of variable 1, a main effect of variable 2, and then our single interaction between the two variables. But what if we add a third variable? Let's just say we have a 2x2x2 design. I want you to pause the video here for a minute and think about How many main effects would you have? That's the easy part. And then how many interactions would you have? How many different ways can our variables interact with each other? That's going to be more difficult to sort of conceptualize. So pause the video, take a minute and really think about that. Maybe write them all out, right? Variable 1, variable 2, variable 3. Write out how many interactions you think you can have, and then hit play when you're ready for the answer. Okay, hopefully you're back. And we're talking about how many main effects and then interactions we're going to have in this 2x2x2 design. So we have 3 main effects, right? Main effect 1, main effect 2, main effect 3, one for each variable. Now let's go through, because there might actually be more interactions than you think there can be here. Variable 1 can interact with variable 2, so that's one interaction. Variable 1 can interact with variable 3, so that's 2 interactions. Variable 2 can interact with variable 3, so that's 3 interactions. And then we can have a 3-way interaction where all 3 variables interact with each other, meaning we have 1 interaction, 2 interactions, 3 interactions, 4 total interactions when we add a third variable. So in addition to our 3 main effects, we would have 4 interactions to interpret. So 7 effects that will be produced by a 2x2x2 design. So when we only have 2 independent variables here in the first example, we have 3 effects. The addition of 1 more variable moves us from 3 effects to 7 effects that we need to interpret. So again, we sort of mentioned previously this idea of complexity. Complexity is good when it helps us understand things we wouldn't otherwise understand. But 7 effects is a lot. That's a complicated experiment. Interpreting each of those in turn 7 times, and then interpreting, just sort of taking a step back and figuring out, what does all of this mean? Maybe, you might have 2 main effects and 3 interactions. How do you report that? How do you convey that information to people? What's the take-home message? Suddenly, interpretation and communication become very complicated. It's certainly possible and plausible, and people do these 3-way interactions and 3-way factorial designs, but you have to be really careful about the way you communicate about them, because they are really complicated. They can be done, and they are often worthwhile, but they take a lot of work and they take a lot of effort and a lot of attention to detail. We're going to be spending most of our time on these, what we call 2-way or factorial designs with 2 independent variables. But just know that 3-way designs are plausible, they're possible, they do occur. The addition of a 4th independent variable in a 4-way factorial design is something that you don't see very often, because there the complexity just kind of goes off the rails. Right? 3 effects is very manageable. 7 effects is manageable but complicated. The addition of a 4th variable is just oftentimes a little too much for its own good. So you typically will not see those. And here's the answer that I just gave you. Okay. So that's the end of section 2. We will pick this back up with section 3, where we will sorry, I went back to that slide on accident. We will be moving forward to working with what are called marginal means and ANOVA tables. Here we're going to start taking some steps for our interpretation of these factorial ANOVAs to not just sort of be conceptual or theoretical like they've been, but we're actually going to move into looking at some numbers, looking at some math, and then starting to interpret for statistical significance using our ANOVA statistical test, which we need for factorial designs. So thanks for listening. Pick back up with section 3 when you have the time, and we'll move forward and get into the world of significance testing. Thanks, everybody.